Tall stacks and plume rise are based on design parameters. And to design, these simple procedures are often followed. First, we have to analyze the meteorology. Second, we have to make a preliminary hazard assessment based on meteorology. Third is test various cases of physical stack parameters, height and diameter, plume rise models, plant locations in conjunction with the worst-case meteorology. Fourth is to consider effects of local terrain. And lastly is to review your results, whether they make sense or not. And on the right, there is equation 20.11. This equation demonstrates that with everything else constant, the concentration at any point, X should go down very quickly as H increases. And table 20.5 is the height of tall things, which is often used as a guideline for designing. Modeling the rise of a plume of gases emitted from a stack into a horizontal wind is a complex mathematical problem. Plume rise depends not only on such stack gas parameters as temperature, molecular weight, and exit velocity, but also on such atmospheric parameters such as wind speed, ambient temperature, and stability conditions. Several published accounts compare plume rise models with each other and with actual observations. Figure 20.13 is the comparison of various plume rise models. Next, we have one well-known plume rise equation, which is the Holland formula, which at one time was recommended for use by the US EPA equation. And equation 20.12 describes the Holland formula, where Vs equals the stack velocity, U is the mean wind speed at stack height, ds is the stack inner diameter, Pa is the atmospheric pressure, Ts stack gas temperature, Ta atmospheric temperature. Next, the last term of the Holland formula is directly related to heat emission rate. It could also be written as equation 20.13, where QH equals to heat emission rate in megawatts. Then another model with reasonable performance is the modified Conco formula, which is equation 20.14. Next, the plume rise as a function of downwind distance x can also be calculated by using equation 20.17 and 20.18. Then the buoyancy flux term Fb given by Briggs in 1975 can also be calculated using equation 20.19, where Fb equals to the buoyancy flux, G is the gravitational constant, MWs is the molecular weight of stack gas, P0 equals the standard sea level pressure. Now for stable conditions, first a stability parameter S is calculated as follows using equation 20.20, where delta theta over delta Z equals the potential parameter gradient and S equals to the stability parameters. Equation 20.21 and 20.22 are the calculations for delta H. To calculate the critical wind speed, we have to use equation 20.11, and from the equation, the pre-exponential term is inversely proportional to U. It was also shown that delta H, and thus H, is inversely proportional to U as well. Maximum Cmax exists at some wind speed of UC, called the critical wind speed. Solving for Cmax for various wind speeds and plot the values of Cmax versus wind speed, the plot will trace a smooth curve passing through the maximum. There are also some other stack design considerations that we have to take into consideration. Now, as air blows past the structure, a low pressure region forms behind the structure, resulting in recirculating eddies and wake formation. In addition, if the structure is large, disturbances in the flow system are experienced above and on either side of the structure. Typical disturbances from a building and from the stack itself are pictured in figure 20.11. These effects may result in plume downwash unless the designer takes steps to compensate for them. Now, figure 20.14 is a depiction of a typical flow disturbances owing to A, a buildings, and B, a stack. The region of turbulence owing to buildings may extend to nearly twice the building height hb and downwind 5 to 10 times hb. A well-known rule of thumb for stack designer is to make the stack height at least 2.5 times the height of the highest building near the stack. Another consideration that needs to be put into designing is the stack cost. For cost estimating purposes, stacks are arbitrarily classified as either short, less than about 120 feet, or tall, which can exceed about 1,000 feet. A short stack is essentially a vertical duct supported in some manner either by its own structure, by an external structure, or with guy wires. The cost of short stack depends primarily on three factors: stack height, stack diameter, and material of construction. The US EPA has developed a simple cost estimation equation as follows, which is following equation 20.23, where C is equal to the purchase cost in 1993 dollars of stack height, D is stack diameter in inches, and AB is the parameters given in table 20.7, which is this table right here. On the other hand, we have tall stacks, and because of the additional components, tall stacks are much more expensive. The cost of a tall stack is more site-specific than that of a short stack, and we can calculate the cost of tall stacks using equation 20.24, where C equals to the total installed cost, millions of dollars, H equals to the height of stack in feet, AB equals to the parameters, function of diameter and liner material, given in table 20.8. Shown here is table 20.8, which is the cost estimating parameters for tall stacks. For computer programming of dispersion models, Gaussian-based models are usually used to represent statistical and means of the observed phenomena of pollutants being diluted and dispersed in the open atmosphere. Various modifications of the basic Gaussian equation have been made to account for such things as elevated inversions, line or area sources, and topography. The dispersion parameters were determined empirically over only a limited range of conditions, and the Gaussian approach is far from perfect. So then, why do we use Gaussian-based model? Well, it's simple. First is because it is easy to understand and apply, and second is because the mathematics are relatively simple and easily adaptable to computer programs. Now let's proceed to mobile sources and line source models. Mobile sources emit large amounts of CO, NOx, and VOCs. Light-duty vehicles such as automobiles, SUVs, vans, pickups, and motorcycles are the largest subgroup of the mobile sources and emit the lion's share of these pollutants. Since emissions of pollutants vary with the type of vehicle, the type of driving, the age of the vehicle, the pollution control equipment, the degree of maintenance, and other factors, one of the problems in the modeling of vehicle emission then is to determine a fleet average emission factor. A fleet average emission factor is calculated for a current or future year, taking into account the age distribution of vehicles, the deterioration in engine and control device efficiency, the driving cycle, and other variables. Now figure 20.16 shows the finite length line source FLLS model. Once again, let us consider the FLLS shown in figure 20.16. A uniform average emission rate Q is defined for the FLLS. The x-axis is parallel with the wind and passes through the receptor. The y-axis is collinear with the FLLS, which is perpendicular to the wind. If the road is not perpendicular, a series of small equivalent FLLS can be drawn that are perpendicular to the wind. Now the differential concentration at the receptor owing to the differential element of the line, which can be treated as a point source, is given by equation 20.25. Now since sigma y and sigma z are constant with respect to y, equation 20.25 can be integrated over the FLLS and written as equation 20.26, where K can be calculated using equation 20.27. Now equation 20.28 describes y over sigma y as b, and by substituting equation 20.26 for y, the result is we get equation 20.29. On the other hand, equation 20.29 can also be written as equation 20.23 or equation 20.31, where g2, g1 equals to the Gaussian distribution function evaluated at b2 and b1 respectively. Overall, in conclusion, we can say that the best mathematical model to be used to represent atmospheric dispersion model is the Gaussian model, owing to its reliability and simplicity in the mathematical computation. This is also the most widely used model for computer programming when it comes to modeling the pollutants dispersion in air. Mobile sources is difficult to model and the estimation usually have a very large degree of error. A lot of considerations must be made to predict the dispersion of pollutants from a moving source. When it comes to vehicles, fleet average emission is the calculation used for estimating the current or future emission by taking into account the age distribution for vehicles, the deterioration in engine and control efficiency, the driving cycle, and etc., as stated previously. With that, I would like to say thank you for paying attention to these slides.